Hi again, everyone. Chris Tisdell here again. Thanks for tuning in. In this presentation, I'm going to continue my series of live streams on mathematics. And I'm going to talk to you about a test for infinite series called the comparison test. I'm going to step you through a couple of examples and then I'll briefly describe why it works. So let me share my screen with you and we can get down to business. Okay, so this is the example I'm going to discuss. Which of these series converge and which diverge? There's, say, a first infinite series and a second infinite series. They both involve the natural logarithm function. This ln means natural log to the base e. And as we'll see, this comparison result basically involves you comparing these summands with something else. So to summarize, this comparison test basically involves a comparison of the summands via an inequality. Okay, now it's a little bit delicate in coming up with these new things to compare with what you've got. So let me step you through the first one, and we can have a look. All right, so log n. We are going to use we're going to use an important inequality involving the natural logarithm function. Now, log n is less than, well, that's strictly less than, I guess, this function n for all n greater than 1. Now, that is a basic fundamental inequality with the logarithm function. So let me just sort of share a little GeoGebra sketch here. All right, so here is the logarithm function. Here it's not just for natural numbers n, it's for all sort of real values. And if I put in the x function, then you'll see the blue curve, the logarithm function, always stays below the red curve, the x function. Okay, so that's an important inequality, at least in this instance, to remember. All right, so let's get back to it. Now, what I'm going to, starting from that basic inequality, what I want to do is get, say, this left-hand side to look like this summand. So what I can do is divide both sides by n cubed, and n's positive, so I don't need to worry about, which way the inequality sign's going to go. So the inner monologue here is to try to get this left-hand side to be this. Okay, so we get n, so we're basically dividing both sides by n, and I can cancel off one of these n's here, and I get this. Okay, so this is for all n, say, greater than or equal to 1. All right. So now we have an inequality involving our summand and something on the right-hand side here, which when we sum both sides up, this right-hand side is a well-known series which we know converges. In fact, in a previous video, I talked about this series here, which when we sum that up will become that. This is a convergent P series with P equal to 2, okay? So we have something that's familiar there. We know this bigger series converges, and the conclusion of this comparison test is that the smaller series must also converge. Okay, so let's just write down a couple of things here. Okay. All right. Now, what can we say? Well, this is a convergent P series. This forces this to be also convergent. Okay, so we recognize that this is a convergent P series with p equal to 2, which is strictly greater than 1. Okay. All right. And what this means is it forces the smaller series to converge. Okay. So let's make that conclusion. So since this bigger series converges, our smaller series also converges. And this is, and so if you wanted to state it, it's a comparison test. Okay, so let me make that nice and clear. All right, and the idea is the comparison test. All right, so that's one element of the comparison test. If you can compare your series with a larger series, where you're basically comparing the strands, right, the sequences, and the bigger series converges, then that forces the smaller series to converge. Okay. Now you can do it the other way. You can talk about divergence if you just have the inequality going the other way. So that's what this second example is designed to show you. So let me show you. Let's step through this. Here we've got this logarithm function again and dividing by n. So instead of starting with the inequality like that, we're going to reverse it, okay, and show that the smaller series diverges. That pushes the bigger series off to diverge. Okay. Now you may be thinking, why does it work? Well, I'll show you at the end. Okay, I'll give you a brief explanation at the end. So bear with me. Okay, so let's get on to part 2. Let's take a new page. All right. Which series so the first series converged. What will the second series do? Okay, so again, let's think of an inequality for the natural logarithm function. Okay, we know from here the logarithm is bounded by this, log of n is bounded by n. Well, we don't want that here. We want something that's sort of the inequality going the other way. So let me just share my Geogebra screen with you again. Okay, so this is from the earlier one. Okay, so I'll get rid of that. There's the logarithm function. And now, if I put in the horizontal line, y equals 1, you'll see that the blue line starts off below the orange line, but at a special point, e 2.7183 approximately, they cross, right? And then the blue curve stays above the orange curve. Okay, so now we have an inequality going the other way for this logarithm function. Okay, so let me show you that. All right. Okay, so we've got this inequality here where 1 is less than or equal to the logarithm of n. Again, that's from the Geogebra picture that I just showed you before. Okay, here. Okay, now how do I get from here to here? Well, let's divide both sides by n. Okay, so 1 on n is less than or equal to the natural log of n all over n. Again, for all, say, n greater than or equal to 3. Okay, so now from this, if I say sum up, I'll keep the inequality. This smaller series is again a p series, okay? But in the first instance, we had a power of 2. Now we've got a power of 1. We know that that series from an earlier video diverges. So the smaller series, if you like, diverges. That pushes the bigger series off to also diverge. Okay. All right. Okay, now this, like I said before, is a P series. It's a divergent P series with P equals 1. Okay. And we can now make our conclusion. Since this series diverges, our original series log n on n also diverges. Okay, and again, if you wanted to name the test, it's a comparison test. All right, so let me just highlight that. Okay, so that's our conclusion. This series diverges. Okay, so let's just recap the main points. We were given when you're given a series, and you can easily form an inequality with, let's say, another sequence or series where you know the behavior. A P series is a really good thing to compare it with. This comparison test says if you're comparing it with something that's bigger and the bigger thing converges, then the original series must also have the same behavior. It must also converge. On the flip side, if you're comparing your series with a smaller series and the smaller series diverges, then your original series must also have the same behavior, must also diverge. Okay, so now in a nutshell, why do these things work? Okay, so let's go back to the first series. Okay, all right, so here we have a series of, say, positive or non-negative terms all added together. Okay, now if you consider the sequence of partial sums, so instead of adding off to infinity, if you like, you put, say, capital N here, and you form a new sequence of partial sums, S sub big N. Now, S sub big N is an increasing sequence, okay, because you're adding positive terms, right? So we know that an increasing sequence will converge if the sequence is bounded. You know, there's some sort of ceiling on it. All right. So that's known as the monotone convergence theorem. So if we can find some sort of ceiling or some sort of bound for that series, we know it's already increasing because it's adding positive. The sequence of partial sums is just adding positive terms. Then we know it converges, right? So where does that bound come into it? Well, it comes in. Okay, comes in when we have this here. This is a convergent series, and so the sequence of partial sums associated with this P series must converge, right? And every convergent sequence must be bounded. So that means the sequence of partial sums associated with this is also bounded. Okay, and you can sort of talk about a sort of analogous thing for the second case. We talk about the divergence. Okay, this is the sequence of partial sums associated with this is increasing and it diverges. Okay, so it has to be unbounded. So the sequence of partial sums for this one is increasing unbounded and therefore must diverge. Phew. Okay, that was just a little explanation in a nutshell. All right, but probably the most important idea to remember with series, especially when you're talking about series where you're adding positive terms, is that they're always increasing sequence of partial sums. Okay, and if you can find a bound or a ceiling on that sequence of partial sums, then it's got to converge. Anyway, hope you enjoyed this video. Thanks for watching, everyone. If you have any comments, any questions, I love reading your comments, so you post them in the comment section or send me a message. See you later for more live streams on mathematics. Hope you can join me soon. Bye.